Let's look at this example problem where two carts collide and stick together in the collision. The problem's asking to find the final speed of the carts after the collision, and it's also asking about the kinetic energy lost in the collision. Let's start with drawing a picture. So if we have two carts, let's have one cart right here. All right, it's moving. Here's the other cart before the collision. Draw my little three-dimensional cart. All right, and one's going this way, one's going that way. All right, so we have a head-on collision. Let's say this is the 5 kilogram cart, and this is the 3 kilogram cart. All right, one of them is going 6 meters per second, and one is 2 meters per second. So they said respectively. So this one's going to be going 6 meters per second. So I've already kind of drawn it wrong. If you look at these vectors, again, this is going to be only 2 meters per second. So let's draw a bigger vector arrow. Now, the carts I actually drew one bigger than the other, but maybe this one's a little more massive. It's got extra stuff in it. All right, so there we go. So we've got a 5 kilogram cart, we have a 3 kilogram cart. They're moving towards each other. This is happening before the collision. So we're dealing with momentum. We want to look at what is happening at the instant before the collision and then the instant after the collision. All right, so there's before. Let's draw the after situation. So these carts, they collide, and it says they stick together. It's a special kind of collision. We call that, it's not only inelastic, meaning it doesn't bounce, but it's perfectly or completely inelastic. So it's perfectly, or sometimes called completely, inelastic. And what defines inelastic is that kinetic energy is lost, right? Remember, energy is not lost, it's conserved, but you can lose kinetic energy, and the rest of the energy is lost to heat, which is really hard to capture, right? So in this case, we're dealing with kinetic energy. We're going to lose some because it is a perfectly or completely inelastic collision, which means at the end, you've got one card here, one card here. They're kind of stuck together. Right, they've collided. And what we don't know is, well, after this collision, they're moving. Now, intuitively, you've got a more massive cart on the left, moving at a faster velocity, hitting a lighter cart, moving slower. Our intuition says that, hey, we're going to have a final velocity moving to the right. And at this point, let's make sure we define direction here. Let's say that moving to the right is now our positive direction, right? When we're dealing with momentum, you want to make sure that all your velocities, they're vector quantities. And so anything left is negative, anything right is positive. So these carts are now moving, and they're stuck together after the collision. So let's set up our momentum equation. What we do know is that the momentum of our system before or initially is equal to the momentum of our system at the end. Right? When we say system, we're just looking at what masses are interacting. Well, it's two carts, which means we can say, well, therefore, the momentum of cart 1 before plus the momentum of cart 2 before has to equal the momentum of cart 1 after plus the momentum of cart 2 after, right? You have two carts. Let's call this 1. Let's call this 2, right? 1 and 2. If you just add them up, you have your total momentum. But remember, P equals mv, which means I can say the mass of 1 times the velocity of 1 at the beginning plus the mass of 2 times the velocity of 2 at the beginning is going to be equal to the mass of 1 times the velocity of 1 at the end plus the mass of 2 times the velocity of 2 at the end. But remember, they stick together, right? When they stick together, those two masses combine, and they're going to be moving at a single final velocity, which means that V final 1 and V final 2 are the same V final. They are both just V final, which means we can factor that out, and you get M1 and M2 being factored out or combined on the right side of that equation. All right, so you're going to see that with these completely or perfectly inelastic collisions, where the algebra actually gets you a scenario where you can visually see that the two masses become one combined. You add them up. All right, so at this point now, we can start plugging in some numbers, right? We've got a basic equation, right? M1 is 5 kilograms, moving to the right at 6 meters per second. Anytime you write a velocity, put the sign with it, just to be careful. Plus the second mass, 3 kilograms, moving to the left at 2, right? And again, there's that negative sign. And that has to be equal to the combined masses, 5 kilograms plus 3 kilograms, moving at some final velocity. All right, now we got some simple math. 5 times 6 is 30. Kilogram meter per second squared of momentum minus 6 is equal to 5 plus 3 is 8 times v final. 30 minus 6 is 24 is equal to 8 v final, which means the final velocity, it ends up being positive 3 meters per second, right? And what does that mean? Well, if you look at my picture, I assumed because the more massive cart was moving to the right, that we would be moving to the right at the end. And in fact, the math tells us that since we get a positive answer, these carts are moving to the right together at 3 meters per second. Had we gotten a negative sign, then I would have known I drew my arrow incorrectly, and then the arrow would have to be to the left. All right, so our final speed here at the top is 3 meters per second moving together to the right. Now, what about the kinetic energy? Well, because it's inelastic, we know we lose energy. Well, with kinetic energy, if we want to find the lost kinetic energy, we need to know how the energy changes. So we need to look at the kinetic energy of the system before, and we need to compare it to what it is after. Well, this system before would be the kinetic energy of cart 1 before, plus the kinetic energy of cart 2 before. And those are just equations. 1/2 m1 times v1 before squared, plus 1/2 m2 times v2 before squared, right? I can evaluate the total kinetic energy of our system just by adding up the two kinetic energies. 1/2 of 5 times 6 squared, plus 1/2 of 3 times -2 squared. Now remember, with energy, we don't worry about direction, and the only vector quantities are velocity. That -2 will get squared and become a positive value. 6 times 6 is 36, divided by 2 is 18 times 5. I'll just pull my calculator out here, and 0.5 times 5 times 36. I have 90 joules of kinetic energy for the first cart, plus 0.5 times 3 times 2 squared is 4, 6 joules in the second cart. So I have 96 joules before the collision. Well, because it's inelastic, I know my answer at the end will be less than that. Well, we now know the velocity at the end, and so we can use that final velocity to find the kinetic energy of the system at the end. And that's just going to be the kinetic energy of the two carts combined, right? Which is going to be 1/2 of the first mass plus the second mass moving together at that final velocity. And if I plug in the values, I have 1/2 of 5 plus 3 moving at 3 meters per second squared, which means I have 0.5 times 8 times 9, and I have 36 joules of energy after, which means I lost energy. The energy lost would be the difference. It's going to be the initial energy, Ke of the system at the beginning, minus the energy at the end of the system at the end. Well, we start with 96 joules. We finish with 36 joules, right? And so we should have 60 joules of energy lost in that collision, right? And it turns out when you deal with perfectly inelastic collisions, those are the types of collisions where you're going to lose the most energy. Sometimes you can lose all of the energy, all the kinetic energy in a perfectly inelastic collision. Now, remember, an elastic collision would be defined as one where you lose no energy. These carts would have the same amount of kinetic energy in the system before and after if it was elastic. But we're dealing with something that sticks together. It does not bounce. It's inelastic. And in this case, when they stick together, it's perfectly or completely inelastic. All right, so our final answer here was 60 joules of energy lost. those carts are moving at 3 meters per second, together, stuck together as one unit to the right.